So here we have a relatively simple FDS model of a small computer room. The computer room has a door at the far end and 5 cabinets along one wall. In the opposite wall there is a small fan which will be triggered by a VESDA system which we will be installing over the top of the 5 cabinets. A point detector is included on the ceiling which has an alarm threshold of 5% obscuration meter and no delays. We're actually looking at a 3-dimensional model which can be viewed from any angle using the smoke view software which accompanies FDS. What we have done is we've simulated a fire, a small 2.3 kilowatt fire in the middle cabinet, and we can visualize the results of that fire by turning on a couple of slices within the space to reveal the smoke density predicted in a couple of planes. I'll just do that. If we load up a slice file in the ceiling, and we'll load up the slice file in a Y plane, and from these we will be able to actually see how the smoke density actually increases in those two planes. Before we run the simulation, let me demonstrate how a VESDA ASD system can be added to the model using Aspire and AspireSDS. Here is the Aspire 2 program. Aspire 2 lets us define and predict the flow rate and the transport times through pipework and sampling holes of one or more VESDA detectors. In this case we're designing pipework for 2 detectors, a VESDA VLC which will protect the 5 cabinets, and a VESDA VLF which is going to sample from 2 holes in the ceiling of our computer room. In here we can see the predicted transport times for each of the 5 holes, and here is the flow rate and the hole's effective sensitivity of each individual hole. We can view a 3D representation of the pipe arrangement which clearly shows the detector with 5 sampling points along a simple straight length of pipe. And it's this arrangement that we effectively want to drop into our FDS model with the relevant transport time and flow figures for each hole. Of course we can also view the 3D representation of the VLF detector which provides 2 sampling holes in the ceiling. All this data is simply saved and can be imported into our FDS model. The software that we actually use to import the data into FDS is of course the new AspireSDS tool. We actually use this tool, here it is, we actually use this tool to create the model that I first showed you, including the main room space and including the 5 cabinets in the space, the fan, and define the positions of the door and the burner, etc. We also define the position and the characteristics of the optical detector. And what we need to do now is to import the VESDA detectors from the Aspire 2 that we created in the background. And that's simply a case of importing the Aspire data that we saved earlier. And of course we have to tell the software where to position each detector in the model space. The VLC detector sits 4.5 meters from the left hand corner, it sits in the plane right in front of us, and it sits 1.6 meters up the wall. The VLF detector on the other hand only sits 2.5 meters from the left hand corner, it sits on the wall closest to us and has a Z coordinate of 1.6. As soon as we've done that, with minimal effort we've imported all the relevant data into our device list, and by simply saving this file we also we create the input file for FDS, which ultimately defines all the necessary parameters to simulate that 2.3 kilowatt fire in the middle cabinet. Back with the smoke view software, we can now visualize the position of the VESDA detectors that have been imported from Aspire 2. If we just reveal the devices that have been imported, these green dots represent the position of the VESDA detector and the sampling holes. It's probably easiest to see this by recalling the 3D representation that we saw in Aspire, where we have the detector and 5 holes, and here we have the detector and 5 holes. Similarly, we can see the detector and the 2 holes for the VLF, here with the 2 detectors on the ceiling. If we now run the simulation from this point, what you will see is you'll see smoke begin to emanate from the top of the cabinet, which is picked up by the VESDA, and the VLC is the first detector to go into alarm. That triggers the fan on the other side of the room as we originally intended. Smoke travels across the ceiling and is sampled by the VLF sample holes, and it's the VLF that is the next detector to go into alarm. The smoke concentration then continues to build up across the ceiling, as you can see by the denser colours, until eventually the optical detector is operated. Now this simulation is very simple, and the main objective is undoubtedly to demonstrate the power and usability of AspireSDS. However, while the fire is relatively simple and the geometry isn't complex, the fact is that the VESDA detectors with their sensitivity of 0.2% obscuration per metre will detect the fire much sooner than the point detectors with a sensitivity of 5% obscuration per metre. So the great thing about AspireSDS is that it's a tool that makes it much easier to embrace the power of FDS to help quantify the anticipated benefits of using a VESDA system. As such, AspireSDS is an essential tool for fire engineers involved in performance-based design.